thank you very much for the invitation to speak today. I'm really happy to be able to come and share some of my research with you. And you're right, the talk title is broad, looking at fault strength evolution during the seismic cycle. But during the talk, I'm going to break it into two main parts. And the first part is going to be looking at sort of the long-term steady state strength of faults. And in particular, I'll be thinking a little bit how fault heterogeneity influences that. And then in the second part of the talk, I will talk about fault strength evolution during, but also after an earthquake event has occurred. But I should also take the opportunity to thank some of my various collaborators who have helped with the bits of work that I will present today. But before I get stuck into some of the research that I've been doing, I'd give you a very brief but overview of some of the sort of fundamental things we've learned from lab experiments about fault behavior, fault frictional behavior. And the obvious place to start is with the work of Jim Byerlee, who showed in his classic paper that most geological materials have a friction coefficient of between 0.6 and 0.85. We don't tend to find many materials or any really geological materials that have friction coefficients higher than this. But the eagle-eyed amongst you will notice that on his famous plot, there are a few materials that fall below this trend with friction coefficients weaker than 0.6. And these minerals are phyllosilicate minerals. So we do have some materials that are a little bit weak, but most geological materials follow a Byerlee friction rule. And this has been widely used to help us with our understanding of fault mechanics and also crustal strength. I'm sure many of you are familiar with plots like this, lithospheric strength profiles, where the upper part of the lithosphere is in the brittle regime, and the Byerlee's rule is used as a sort of maximum bound for the frictional strength in the upper part of the lithosphere. And then as we go down with depth, we go through the brittle ductile or the frictional viscous transition, and then we end up being dominated by temperature-sensitive deformation mechanisms such as crystal plasticity. But in terms of how strong faults are in nature and whether they follow Byerlee's rule or not, there is contrasting evidence. Some faults or some studies have shown evidence that faults are strong and they follow Byerlee friction, so such as stress measurements from deep crustal boreholes. They have been shown to suggest from intraplate fault systems that you can get Byerlee friction values. But there's other evidence from, for example, heat flow, lack of heat flow anomalies, or from, in this example here, of force balance calculations at convergent plate boundaries, that we get much weaker faults. And in these subduction zones, the shear stress that the megathrust is operating at is calculated to be much less than would be expected for if Byerlee friction was in operation, suggesting we have much lower frictional values. And possible explanations for weak faults in nature include localization of those weak phyllosilicates I showed before in the Byerlee friction slide, or maybe high pore fluid pressures, which lower the effective normal stress, making the fault appear weak, or various other reaction mechanisms that potentially weaken the fault. And if you want more of an overview of this sort of strong versus weak fault argument, there's a good review paper by Cristiano Colattini that came out in 2019 in Earth and Planetary Science Letters. And in that work, they suggest that we should probably move away from thinking about faults as either strong or weak, and move towards thinking of them as both structurally and frictionally, structurally and mechanically heterogeneous, with strong and weak patches. And this is something I'll come on to talk about a little bit later in the talk. And so the final thing I want to do, talk about in this brief overview about what we've learned from the laboratory, is what happens to fault strength when we move away from slow slip rates up to slip rates associated with earthquake events, which is typically on the order of a few meters per second. And this is a classic plot from Di Toro, who shows that the friction rates, as you approach meter per second rates, the friction values drastically decrease. And that's due to various dynamic weakening mechanisms becoming activated due to shear heating or grain size reduction along the fault. But I'll move on now to talk about some of my research, and in the first part I want to think about how fault rock heterogeneity controls fault strength and stability. And the motivation for this is that faults are intrinsically heterogeneous over many different scales, from sort of sub-millimeter foliations up to, I've got a couple of examples in part A and B here of sort of centimeter scale heterogeneities. We've got shear clast here in sandstone at Punchbowl. We've got sheared layered foliations here on the centimeter scale. But then we get heterogeneities at much larger scale. So this is a photo in panel C of a sort of section through the Carbonara strike slip fault in southeast Spain. And this is a fault zone. This is the fault core we're looking into, which is several hundred meters wide. And you can see these different colors correspond to different lithologies within that fault core. And we can go all the way up to the plate scale. Heterogeneities are often invoked, for example, in subduction zones, to act as potential earthquake nucleation sites, such as, sea mounts on subducting slabs. So we get a broad range of heterogeneity of nature, and I wanted to try and test in the laboratory how that affects, fault strength and stability. And although it's never really going to be able to test the complexity of heterogeneity that we see in nature in the laboratory, I wanted to try and just see how a simple heterogeneity affects fault strength. And this is an image of our, or a diagram of our experimental setup. There's quite a lot of information here, but basically what I did is I took layers of fault gouge, which is shown in the middle here, separated into patches of different types of fault gouge. So basically I create heterogeneous layers by just placing different patches of fault material next to each other along our experimental fault here. And then the layer is sheared by these direct shear sliders, which have an internal plumbing, meaning we can control the pore fluid within the gouge layer. And then this setup is jacketed and put inside a pressure vessel of a triaxial rig, and the confining pressure applies a normal stress to the fault. And then we use the axial piston of the triaxial rig to apply a shear stress and shear the layer. But in the work I'm about to show you, all tests are run under an effective normal stress of 40 megapascals. All we did was vary the relative proportions of the different materials. We used two different materials. We used a quartz gouge, which is frictionally strong, follows this Byerlee friction rule and is rate weakening. And we use a kaolinite clay gouge, which is much weaker and is also rate strengthening. And we sheared these layers at slip velocities of 0.3 to 3 microns per second. And we stepped back and forth between these values to analyze the rate and state behavior of the fault during the experiments. So we did two types of tests. We did the test with these heterogeneous patches in the fault, and then we took the same materials and we homogeneously mixed them together so we can compare the behavior of heterogeneous faults with the behavior of homogeneous faults. And this is what the mechanical data looks like. On the left, we've got the behavior from these heterogeneous gouge patch faults, and then the homogeneous, on the right, we've got the data from the homogeneous faults where the gouges are mixed together. And you can see the different curves correspond to different clay fractions. The 0% clay, the pure quartz at the top here, has a Byerlee friction coefficient, and the pure clay is much weaker, a friction coefficient of maybe around 0.25. But if we just look at, actually start with the homogeneous faults, you can see after the layers yield, the frictional strength remains relatively constant throughout this entire experiment. We have little perturbations in the curve. These are the velocity steps as we step back between 0.3 and 3 microns per second. But the steady state strength remains relatively constant. Whereas in comparison, the heterogeneous faults, after yielding, all show a progressive weakening, and they weaken towards tend towards the value of the weaker clay phase. So yeah, we have quite contrasting frictional behavior here, or strength evolution behavior of the homogeneous and heterogeneous faults. And you also notice that in the heterogeneous faults, in the pure quartz layer and in the high quartz fraction of the heterogeneous faults, we get these stick slip instabilities also triggered by the velocity upsteps, which we don't see in the homogeneous faults, which I'll come on to talk about in a little bit. But for now, if we just think about this weakening trend and maybe what causes it. Oh, actually, I should also say we first of all, our setup is this was originally a quartz patch bound by two boundary clay patches, and we use this symmetrical arrangement to avoid any misalignment if we get differential compaction between the different gouges. But I did some experiments where I reversed the symmetry and put the clay in the center and surrounded it by quartz, and we see the same weakening trend. So this shows that it's not an arrangement of the patches that causes the weakening, it's the heterogeneity itself that is responsible for the weakening. So why do the gouge layers weaken, the heterogeneous layers weaken? Well, we had to look at the microstructures recovered up to the end of the experiment, and we're looking at an image here at the interface between the quartz and the clay gouge. And you can see that the clay gouge has been smeared out along a boundary Y shear here, and a little schematic diagram here to show that which part of the fault layer we're looking at. So potentially this clay smearing could be responsible for the weakening we're observed. It could be because the clay is localizing, it produces maybe stress concentrations which weaken the gouge, or also if the the total area of the fault surface is increasing, is being increasingly filled with more of the weak material, that will essentially have the effect of weakening the entire layer. But we can predict how much clay smearing there is, or we can calculate what the weakening effect of that would be, because the amount of the clay smears will be proportional just to the displacement of the fault during the experiment. So we calculated how much weakening we expect from clay smearing, and actually it's a very small effect that we see, and that the observed weakening in our experiments is much greater. So there must be something else going on other than just the smearing that's causing the weakening. The other thing we thought about is that if you have a competency contrast between your two different materials, if during shear one of them compacts slightly more than the other, this can redistribute the normal stress along the shearing layer. And if it's the strong quartz gouge that compacts more, then this will transfer stress into the normal stress into the clay patches. And if we look at the volumetric strain data from the M-member tests, we do find that the quartz does compact more than the clay during shearing. And then we performed some back of the envelope calculations, assuming that our forcing blocks are rigid, and making some assumptions about what the elastic moduli of the gouges are. And we find that if we use sort of realistic values of between 2 and 4 GPa for the bulk and shear moduli of the gouge, we find weakening trends which match kind of the observed weakening we're seeing in our experiments. So potentially competency contrast and differential compaction might be responsible for the observed weakening that we see, or it's probably actually a combination of all the mechanisms that I talked about, the clay smearing, potentially some stress concentrations, and the contribution of differential compaction. So now I just want to move on slightly to talk about the frictional stability of the two different types of fault, the heterogeneous and the homogeneous fault. So I showed you we have these perturbations, these velocity steps throughout our experiments. And I'm sure many of you are familiar with rate and state framework, but basically if you're sliding at a steady state friction value and you impose a velocity change, in this case a velocity increase, you get an instantaneous change in the friction, which was this term A, and then that decays over a given distance to a new steady state friction value. And if that steady state friction value is above the previous one, after a velocity increase, we call this velocity strengthening behavior. And if it's weaker than it was before after a velocity increase, we call this velocity weakening behavior. And we look at this term A minus B. If it's greater than 0, it's strengthening. If it's less than 0, it's weakening. And velocity strengthening is considered to promote stable slip on a fault, whereas weakening behavior is considered to be a prerequisite for unstable sliding which is also dependent on the stiffness of your fault materials. So on the right here, we have, I've shown you in panel A and B, the A minus B data for the homogeneous faults in red and the heterogeneous faults in blue as a function of clay fraction. And the two panels A and B are just different displacements from the experiment. And you can see that the homogeneous faults are always consistently more, or have consistently higher A minus B values. So they are more stable than their heterogeneous counterparts. And what we also did is we analyzed for a given clay fraction the difference between the heterogeneous A minus B values and the homogeneous A minus B values, this delta A minus B term, for every displacement throughout these tests. And we find that almost all the A minus B values fall within this lower part of panel C here, which is where delta A minus B, showing that the heterogeneous faults are always got lower values and therefore more unstable than their homogeneous equivalents. So the heterogeneity is not only affecting the fault strength, it's also affecting the fault stability. And I'm just going to briefly take a sideways step away from the heterogeneous faults a minute, just to show you some other results from another study I did a couple of years ago about some of the other controls on frictional stability. I've only got one slide on this. But what we did here is we tested fault gouges collected from the Nankai Trough in Japan via IODP drilling. So we took the same material and tested it over a range of different pore fluid pressure and effective normal stress conditions to see how that affects the A minus B and the stability of the gouge. And we found that once we get to effective normal stresses of above 25 MPa, that A minus B is pretty much exclusively controlled by pore fluid pressure. So in this panel A on the right, on the left here, you can see that for a given pore fluid pressure, the A minus B value doesn't change much as you increase the effective normal stress. But at a given effective normal stress, if you increase the pore fluid pressure, then we found that A minus B actually increases. So the system essentially becomes more stable at higher pore fluid pressure. And the same data is just plotted here in panel B, where you can see we've got pore fluid pressure on the x-axis here instead. And we've got this increase in A minus B with increasing pore fluid pressure again. And we found that is actually related to a change in the B value of the rate and state parameter B. The A parameter is relatively constant and independent of pore fluid pressure, but the B value becomes, the values get lower as the pore fluid pressure increases. So I just want to put this slide up just to show you that, as well as material properties such as whether the fault's made of clay or quartz, or if it's got heterogeneous distribution that affects the frictional stability. Also, the other parameters such as the stress conditions, and in particular the pore fluid pressure, also affects your fault stability. And if you want to learn more about that, I would encourage you to go and read that work in EPSL. But just to go back to the heterogeneous faults and to sort of summarize this first part of the talk, we found that heterogeneous faults are weaker and also more unstable than mineralogically equivalent homogeneous faults. And therefore, this suggests that heterogeneity could contribute to fault weakness in nature. And the weakening effect is probably caused by a combination of mechanisms, some smearing of the weak phase, potentially stress concentrations caused by localization of the weak phase, and also competency contrasts leading to differential compaction and redistribution of normal stress along the fault. And at the large scale, the scale of heterogeneity is likely what's going to dictate whether you get patches large enough for earthquake nucleation or not. But I now just want to move on to the second part of the talk, which is moving away from looking at the steady state fault strength and looking at how fault strength evolves during an earthquake, but actually more focusing on how it evolves after an earthquake. Because we've known for some time now that when faults accelerate to meter per second slip rates, we get this drastic reduction in frictional strength. This has been shown in numerous laboratory experiments. But what I'm actually interested here is how does this frictional strength recover after fault slip has stopped? How does the frictional strength, or how does the fault heal after a seismic slip event? And fault healing is been studied for quite a long time in the laboratory, but typically it's studied at very low sliding velocities, on sort of on the micron per second range. And the way fault healing is studied in these studies is to perform experiments which are called slide hold slide experiments, whereby you take an experimental fault, you shear it a little bit, and then you stop the shearing and hold the fault in stationary contact for a predetermined amount of time, and then you re-shear your fault, and you look at how the fault strength evolves as you re-shear. And you can see some examples of these slide hold slide events here, where the hold time is indicated as the number below, but the peak strength achieved after the initiation of sliding, after the hold, increases the longer it was held in stationary contact. And these studies have shown that generally the frictional healing, the rate of this increase is dependent on the logarithm of the hold time. We get these log linear relationships. So basically in the study, I wanted to take this sort of slide hold slide methodology, but apply it to fast sliding events. And part of the motivation for this came from studies that to document fault healing in nature, which is something that is not easy to do using geophysical methods. But there is some evidence. For example, this study here by Tadakura and Ando in 2002, where they looked at shear wave splitting measurements around the Nojima fault in Japan, which is where which hosted the 1995 Kobe earthquake, and they found that all the damage that had opened up during the earthquake had pretty much healed within 2 to 3 years after the main earthquake event, which is very quick considering the recurrence interval on this fault of large earthquakes is predicted to be around 2,000 years. And there's also other evidence from borehole permeability measurements from the long-mentioned fault in China after the 2008 Wenchuan earthquake, which again suggests the fault healed within a couple of years after the earthquake. So there's some evidence to suggest that faults actually heal relatively rapidly. These are probably different healing mechanisms to the ones seen in slide hold slide experiments. But this got us thinking about whether frictional healing would also be rapid after a seismic event. So this is a sort of framework we're looking at, where we have a coseismic event where we get a dynamic reduction in frictional strength. What I'm looking at is what happens in the post-seismic regime. Do we get a rapid increase in the frictional strength, or do we get a more slow healing of the fault associated with more the classic D-trig type mechanisms we see in slide hold slide experiments at slow sliding velocities? So to perform these high velocity experiments, I used the PHV rotary shear apparatus, which is in JAMSTEC in Japan, the Japan Agency for Marine Earth Science and Technology, where I was based as a postdoctoral fellow for a couple of years. And basically, I took layers of gabbro fault gouge and granite fault gouge and sheared them in this rotary shear apparatus under quite low normal stress at just 1.5 megapascals, and applied a equivalent slip velocity of just over 0.5 meters per second, so approaching seismic slip velocities. And in these experiments, what we did is essentially slide hold slide experiments where they were sheared at high velocity for 15 meters of displacement, and then we held them for various amounts of time and then re-sheared them to see how the stress evolved. And you can see the data from the first sliding event in the experiment. Here we've got the granite gouge on top and the gabbro gouge below, and we see that both gouges have a peak friction of around between 0.7 and 0.8, and then that decreases down to around 0.5 by the end of the first sliding event, which is actually not a very big dynamic reduction in frictional strength, but these are done at not super fast velocities considered compared to other studies, and also at quite normal, low normal stress. So it's actually quite comparable to other studies at these conditions. But if you do it at high normal stress or at higher slip velocity, you would get more significant weakening. And then we held the layers. Each of these curves is a different experiment. We held them all for different amount of time, and we found that in the second sliding event, the peak friction that was achieved is dependent on the hold time during the hold period, with layers that were subjected to long hold times achieving a higher peak friction, which is exactly what you see in low velocity hold slide experiments. But what we want to do is compare the healing rate, and to calculate the healing rate, what we do is we take the peak friction from the second sliding event, and we subtract the final friction from the first sliding event. So we're looking at this difference here and plotting it against the hold time, and that's what these graphs are showing here. This delta mu, the peak friction of the second sliding event minus the sort of final steady state friction of the first sliding event. And you can see that both materials, the granite and the gabbro, actually recover their strength very rapidly. So that sort of 0.25 that was lost during the first sliding event is recovered in about 20 seconds for granite, and for gabbro it's even faster, maybe less than 10 seconds. It's recovered almost all the strength that it lost during the first sliding event. And then after this initial rapid increase in frictional strength, the healing rate decays, and it actually decays to a value that is similar to what is observed in low velocity slide experiments performed at micron per second slit rates. And I've included some low velocity data just for reference here, and you can see the healing rates are of a similar order of magnitude after this initial rapid healing that we observe here. But obviously the big difference between low velocity tests and high velocity tests is you get a lot more shear heating at high velocity. So what we did is we drilled some holes in the top of our experimental forcing block and put some thermocouples through them, and so they were basically touching the top of the gouge layer to monitor the temperature during the experiment. So what we found is that the peak temperature we reached during high velocity sliding was around 350 to 400 degrees Celsius. And then that decays during the hold period. The sample cools during the hold period, but it takes several tens of minutes actually for the temperature to reach the sort of ambient temperature in the laboratory. And if you look, this rapid healing occurs while the temperature is still above sort of 250 degrees Celsius. The rapid healing is occurring while the material is still hot from shear heating after high velocity slip. So I want to move on now to think about maybe what is causing this rapid healing. And the first thing we do is look to the microstructures of the sheared materials. And actually they're not particularly informative in terms of understanding healing mechanisms. You can see the starting materials on the left here of the granite and the gabbro, and then the sheared materials of the granite and the gabbro. And there is a difference. You can see that in the granite, the deformation is pretty much distributed throughout the layer, whereas the gabbro fault does show some localization at the tree. And we have, within both layers, we have rounding of large grains and surrounded by a much finer grains matrix. There's been a lot of grain size reduction via cataclasis. But although there is difference in the localization behavior of the two gouges, actually, you might remember the mechanical data for these materials is remarkably similar. So I don't think the localization is having a particularly strong effect here. And in terms of understanding the restrengthening, there's not much we can squeeze out of the microstructures. But what causes restrengthening? There's sort of two sort of prevailing hypotheses from laboratory friction experiments, is that either at frictional asperity contacts within your fault or in the gouge layer here, you get an increase of the real asperity contact area, or you're potentially getting some sort of chemical bonding effect, which could be restrengthening your asperity contacts. So what we did is we analyzed our sheared materials using Raman spectroscopy, because Raman spectroscopy actually provides information about the chemical bonding state of the surface of your sheared materials. And what we found in both materials is we get a small broad peak in the spectra, a wavelength of around 1600. And what this Raman peak corresponds to is a particular vibrational mode of water that is absorbed on the surface of the sheared materials. And this is something that we don't see in the starting materials or gouges that are sheared at low velocity. So what I did was I took some of the starting materials and heated them in an oven to different temperatures, and then removed them from the oven and let them cool in the atmosphere, the humid atmosphere, similar to how the fault gouge layers cooled within the experiment. What we start to see is the small peak appears at around sort of 300 degrees for gabbro. In granite, it's less obvious, but we start to see maybe a small peak around 250. But these are the sort of temperatures we were reaching in the high velocity experiments. So it looks like we're getting some sort of chemical bonding change on the surface of our gouge materials caused by the high velocity slip. And we hypothesized that potentially it's chemical bonding that is happening quickly after the gouges stop shearing that is re-strengthening the materials. And actually, the story gets a little bit more complicated here, because although we see a peak associated with absorbed water on the surface of the materials, we don't think that absorbed water is responsible for the re-strengthening, because actually, as we showed, the re-strengthening occurred while the temperature was still high, above 250 degrees Celsius, where the water would be in the vapor state. The water will only reabsorb once the gouge cools below maybe around 100 degrees Celsius. So why have we got this change in the absorbed water? Well, what I think is happening is that how water reabsorbs on the surface of materials is very dependent on the structure of your material, of the substrate that it's absorbing onto. And if there's been some chemicals change on that substrate during high velocity shear, which maybe then allows rapid bonding, then water can maybe reabsorb in a different mode once the gouge cools. And there's been quite a lot of work in the theoretical field of atomic simulations that show that when you shear silicate minerals, produce fresh fracture surfaces on them, the silicate minerals are very susceptible to form silanol bonds, which are these SiOH material on the surface of the fracture surface. And these silanol bonds can then produce hydrogen bonding between cross-asperity interfaces once the gouge stops being sheared, or potentially it can also react to form strong siloxane bonds, which is SiO-Si bonds. And this has been, studied in atomic simulations, which show that the kinetics of these reactions do increase with temperature. And it is plausible that we're getting very fast hydrogen bonding on our gouge surface at high temperature once they've stopped shearing, which is causing this rapid re-strengthening. And then once the gouge cools, we get the water absorbing in this change of vibrational mode, which is what we're picking up in the Raman spectra. And we get this change because we've got this change in bonding on the surface caused by this hydrogen bonding. And there is other evidence, to suggest that chemical bonding might be responsible for rapid healing in friction experiments. So there was a study performed a few years ago by Mizuguchi et al., where they sheared bare surfaces of granite, so not gouge, so just bare surfaces, rock to rock experiments. And they did some experiments in the room humidity conditions, and they did some experiments under nitrogen conditions. And what they found is these are slip pulses, slide hole slide slip pulses, and we see the hold time listed here. And under room humidity, we do see the strength recover and the peak strength increasing as it's been held for longer static hold periods. But in the nitrogen atmosphere, regardless of how long they've been held, we don't see the same recovery of the peak strength in the gabbro bare surfaces that we do at room humidity conditions, which suggests there's a chemical effect that is causing the healing in these bare surface experiments. I should say they were conducted at slower slip rates than what I performed on the gauge. These were done at 85 millimeters per second, so more subseismic slip velocities. But they do show that we get a chemical dependence on this healing mechanism. So one thing I tried to do was actually perform similar bare surfaces, but at higher slip velocities, the same slip velocities I performed in the gouge, to see if we get a change in the healing rate, but to compare to the study of Mizoguchi. But what we found is that actually during bare surface experiments, where the deformation is much more localized than it is during the gouge experiments, that the restrengthening actually occurs during the deceleration phase of the experiment itself. It doesn't occur once slip has stopped like it does for the gouge experiments. So at higher slip velocity on bare surfaces, actually the healing mechanisms, whatever they are operating so fast that we get restrengthening during deceleration itself. And potentially, in terms of thinking about rupture mechanics, if we're getting very fast healing mechanisms operating along faults just after they start to decelerate a little bit, this is the sort of thing that maybe could be happening during a pulse-like rupture on natural faults, where you need fast healing mechanisms directly behind the rupture front to re-strengthen the fault and stop it slipping again as it's reloaded from the energy that's been imparted on it from elsewhere in the fault. But regardless of what the healing mechanism is, the summary of this part of the talk is thinking about that we see this rapid healing immediately after a high velocity slip event. This rapid healing occurs while the gouge is still hot, and we find evidence of a chemical change associated with the materials that have been sheared at high velocity, which is potentially suggesting that it's chemical effects that are causing rapid healing on these gouge faults. And our results suggest that if faults can heal rapidly after an earthquake, and they may also, if the healing mechanisms become more efficient as either the gouge, as the fault is more localized, or under higher stress conditions, they could be also important maybe during rupture propagation for the creation of potentially pulse-like ruptures. But I'm almost done. I'll just leave you with, I'll bring back the other figure from my first part of the talk, just to summarize that, in the first part I showed you the sort of steady state strength evolution, the long-term steady state strength evolution of faults, and how heterogeneities can really affect that and make faults much weaker and also more unstable than compositionally equivalent homogeneous faults. And in the second part of the talk, we looked at high velocity friction data and how the strength is recovered after high velocity slip, and we see this rapid healing, which is potentially associated with chemical changes that occur during high velocity slip. So I will finish there and invite any questions you may have. Thank you.